So it's my pleasure to welcome Marco Morandotti from the Replicator, and he is not for the first time here, but he already gave a couple of talks, and I think it's very interesting. His talks most view on our so people viewing our person again. And today we will talk about replicated dynamics of life population when we discrete model.
Thank you very much, Martin, for the presence and remotely. I hope the sound goes through fine. Yeah, as Martin mentioned, it's not my first time, my third time delivering honored and also flattered for the views or on the YouTube channel. But so to talk to you about this topic, which goes with the things that I talked about, like see those as multi-agent systems. And ideally, in multi-agent systems, you might want to describe what happens when you've got agents that move around in the space with some strategies that can be modified over time. Like if you are playing a strategy which you don't like, then you might want to change that. And the position of where you sit can actually influence the success of a strategy against another one, or maybe the same strategy in a different position. And ideally, one wants to be able to track these aspects as well. So one of the models used in population dynamics is the replicator dynamics, which tells you the rule for updating strategies success. And interestingly, it only sees strategies. So strategies are carried by individuals in a population, but the individuals are not present. They are not seen in the replicator dynamics. And only the proportions of strategies that are played is important for these dynamics. On the other side, in the Moran process, the dynamics is you could say microscopic. So you see what happens when an agent is chosen for reproducing their strategy and in a way impose their strategy on another agent. So in the Moran process, it's usually a time discrete Markov chain where the behavior that you've got it at each time step, you select an individual to reproduce its strategy, and then you select another individual to suppress their strategy, and to inherit the individual that's been selected for reproduction. And there's a link between these two types of dynamics because the Moran process sees the population, sees the individuals, whereas the replicator dynamics is just a mesoscopic type of description, and you only see the strategies. So together with Gianluca Orlando from the Politecnico in Bari, we proved that the replicator dynamics can actually be derived as of jewels goes to plus infinity. And there are some other quantities that are involved in this limiting process, which I'm going to talk about in a second. And the first thing that I would like to do is actually to specify a little bit more the title. The really full title should be this one. So there are two more ingredients. One is the so-called weak selection regime, which is a way in which say the fitness is computed for each strategy impacts in the probability of selecting an individual that carries that strategy. And the last part, a proof via Eulerian specification, means that we will have to deal with some sort of the strategies, and there's going to be a notion of Eulerian solution connected to that. So the link will be that when we perform the limit as the number of individuals diverges in the Moran process, then we will get the Eulerian version of the replicator dynamics. So the outline of the talk is just made of 3 items. So what the replicator dynamics is, the description of the Moran process, and the limit process to make the second one to converge to the first one. And the general setting is the following one. So we're looking at n individuals in a population. let me see. Okay, so this one here, and each of them can have can play up to M strategies. So U1, UM are the individual strategies that can be played, and for the rest of the talk, M is going to be finite, and the set the curly U of strategies is just going to be that one. So in the easy case where M is equal to 2, you could think of strategies as expressions of a gene, and you might have a dominant allele or a recessive allele, as we always study in biology in high school. And you should see that the dominant dominates over the other one. Whereas if you take many strategies, it could be something like multiple expressions of something, and the very hard task would be to do one further step into the generalization, and U is substituted by a compact metric space. So you could allow for continuum strategies. For instance, if you measure height and you see the height as a strategy, or the length of the neck of a giraffe, that spans over a continuum of values. Then another ingredient would be the payoff of a strategy. So I will denote it by pi of ui, and it tells us how much this strategy gains when it competes against other strategies, and the fitness of the individual with the strategy UI. So it would be best said the fitness of the strategy UI is this expression there, which, if you want to see it, it's kind of a convex combination between the constant one and the payoff UI, because we ask W to range from 0 to 1. And so if W is 0, then we have a so-called pure Moran evolution. So everything is just determined by the fraction of individuals carrying the strategy UI, and that determines the probability of an individual. Whereas the strong selection is where all the fitness is basically due to the payoff of the game. So you have to imagine that an individual plays games with other individuals. They see at which strategy they have, and there's a description of the payoff that records the encounters of these two individuals. And everything happens in a time interval 0t, which will be fixed for the whole talk. And actually, we won't be seeing anything as t goes to infinity, but just a finite horizon. And then when we want to perform a limit, we do it in this way. So we discretize time, and then tau k is the time step. And so we consider sequences of time discretizations paired with the sequences of numbers of individuals going to infinity, and of weakness, of selection parameters going to 0. So the weak selection regime is when W is very small. So it's almost all Moran and very little the payoff. And then we want to perform a limit as tau k goes to when tau k converges to 0, and accordingly the other parameters need to converge. Nk needs to diverge, and Wk needs to converge to 0 as well. Interestingly enough, they cannot converge or diverge independently, but we need to ask behaviors of this sort. So we need to ask that the number of individuals scales like 1 over tau k to power alpha, and that the weakness, the selection parameter scales with parameter tau k to the power beta for positive alpha and beta, both smaller than 1, but alpha needs to be smaller than 1/2. And the red thing is because it's going to be crucial at the end of the seminar, so keep that in mind. And the sum of them needs to be 1. So in this way, we can prove this is the regime, or the link in between the parameters that allow us to prove a result. So you see that if alpha and beta need to add up to 1 and they need to be positive, then the behavior is some sort of a root type behavior for Wk, and also for the inverse of Nk. Okay, so this was just the big picture. Now, the replicator dynamics is, maybe I have only one slide, and it's this typical model which is described in evolutionary game theory books, for instance, the one by Hofbauer and Zygmunt. And it describes the change in time of the, say, proportions of the strategy. So lambda ui, each of those items in that vector, is the proportions of individuals having strategy ui at time t. And then you can collect all of them in a big vector lambda, and you want to study the evolution of that. So how does it work? It works in this way, where you have this object here that basically tells you, so A is a payoff matrix. So basically A, ij is the payoff that you get when you are playing strategy UI and your opponent is playing strategy UJ. All right? And all the possible games that your opponents make. And then you subtract the scalar product of that thing with lambda itself, which basically averages out all the possible other games that I can play. So this tells me the performance if I choose UI against the average. So this one into the brackets is a number, and it can be positive or negative. If it's positive, it means that my strategy UI, the one that I'm looking at, does better than the average, so I might want to choose it because it gives me a better payoff. If it's negative, then the time derivative is negative, and then what this is saying is that I'm suppressing it because it's not worth choosing that one if I want to maximize my payoff. Something else will do better than that. And so you can make that explicit in this form, and that's precisely what I described. So this one builds up a vector field B for the time derivative of lambda, all right? So then you need to multiply it by lambda UI. If this is not zero, if this is zero, it will never become different from zero. So assume that it's not zero, you can divide, and in the left-hand side, you will be left with the derivative of the logarithm of lambda UI, fine. And then it can be positive or negative. And as I mentioned before, while introducing this problem, this is a sort of a mess. Then I not see the individuals carrying the strategies. And this topic has been already addressed in this paper that I started with Ambrosio Fornazier and Savare, and then I extended a little bit with Francesco Solombrino, just to find optimal, say, hypothesis. In both those papers, we actually look at something a little bit more sophisticated because we do not only have evolutions for the strategies, we also have spatial dependence as playing a strategy, I don't know, enable the outcome with the same strategy. And there's also relevant for this talk at the moment. Okay, now let's go microscopic and let's see the description of the Moran process. So I have a population of agents that were capital N. So here it's capital A, that's for the agents. They are labeled by 1 through N. There's my usual time step, and there are the strategies. And the states are probability distributions over the space of strategies. So there's basically convex combinations basically of the UIs. And I can identify the probability space of probability measures over the strategies with the simplex, like the n minus 1 dimensional simplex, because they need to be all positive. It's not written there in the green, but they need to be all, say, non-negative and add up to 1. Then I have a payoff matrix, and this one is basically the probability for an agent to be selected for a production. So that for a production is proportional to that thing which is the fitness. And the fitness is a convex combination of 1 and the expected payoff of the strategy carried by the big disk. Then I uniformly select an agent for whose strategy needs to be suppressed. That may be a little bit too harsh, but that's so that the yellow or orange one will become green in when the game has ended. And so this is called a birth-death process, because first you select the agents that reproduces the strategy, and then you select uniformly the agent whose strategy is suppressed. And we can build up an evolution for this, which is going to be a piecewise constant curve, which I call lambda t, depends on a bunch of parameters, which is a probability measure on the space of probability measures. So just in this case, because we have a finite number of strategies and we can identify P of U with the simplex, this one is a little bit more simple to study. Otherwise, the tools that I developed with Savare, Fornazier, and Ambrosio will be those really needed to study the dynamics in P of U, if U is a compact metric space. So let's look closer a little bit at the dynamics. I want to see what's the probability of selecting agents with a given strategy. So it's written down there basically. So the probability that an agent carrying strategy UI is selected for a production is given by that expression. So basically, I renormalize by the number of individuals carrying the strategies with the frequency gives me the probability of success for this event. Whereas the probability of selecting another individual for inheriting, so for abandoning the strategies, is just the number of those carrying the strategy divided by the total. This is the uniform one. Okay, and this determines, as it's written, that the probability that the number of individuals carrying strategy UI increases by 1. All right, so what I'm doing is that at time th, I'm taking a picture. I see precisely n subscript I in the little n I individuals with strategy UI, and then with this, like given that state, I compute that the probability that at the following time step, the number of individuals carrying UI has increased by 1. F is the fitness, which is computed in this way. So the rule for the payoff I gave you before already a couple times. The payoff now is given by this expression here, which counts the encounters that you can make. So basically, if I am an agent carrying strategy UI, then I can meet n-1 other agents. So that's explained in the denominators. N of UI minus 1 of which have my same strategy. And so this accounts for the elements in the diagonal there. And n of uj for j different than I are those carrying any other strategy. And given each uj, then I have the payoff given by A of ij. So in this way, the payoff is determined by binary interaction. So each individual meets all of the other ones, and the dynamics happens in this way. There could be different models, just to mention that if you don't have the possibility, or if your model doesn't allow for interacting with all the individuals, like the fitness of, I don't know, my black hair is hardly decided by people that are in Japan. So I don't really meet them. So maybe you want to have a cutoff or like a radius of interaction, which can model this sort of interaction, and the fact that not all of them are possible. Okay, and the proportions vector lambda evolves in the following way. So at each time step, we have that amount. So the NUI divided by n is that. And when I want to see the evolution of it as a measure on the simplex, then I need to look at the associated empirical measure. So given my strategies U1 through UM, I can construct this empirical measure mu tau mu, which is the convex combination of deltas, each of which is centered at the UIs. And this is genuinely an element of P of U, but if you look just at the weights, it's an element of the simplex. That's why the identification is possible. So you want to start with a given array of proportions, lambda 0, and then you want to build the capital lambda 0 as I described before, and then the evolution is precisely given by that formula. So basically the lambda 0 at the capital lambda at the initial time is the push forward of through the vector of weights of a reference probability measure that I put on the say that there's always omega fp like a probability space, because all these are random variables. So I do the push forward of the reference probability measure, and this describes a probability measure on the simplex. Now, replication and death are the crucial items to study the dynamics. So the state of the system is a random variable. Here RV stands for random variable, and it's a vector that tells me S1 at time t, Sn at time t. So for each of the n individuals, they tell me which strategy they are playing. So it's with values in u to the power n. So each element is a u. So it's a strategy. I take a picture of my system, and then I say individual 1 is having strategy 3. Fine. And then each of the realizations that I might want to measure, that I might observe, are denoted with a hat. So as hat is what I observe, and without the hat is still a random variable. And now I need to define two more random variables, one that describes the individual that's chosen for replication, and one that describes the individual that's chosen for abandoning the strategy. And I denote them by capital R and capital D. And so I need to check the probability that given my picture of the state at time h being equal to time th, sorry, being equal to s hat, then at time th plus 1, the individual chosen for replication is n, is a certain n. For any n that belong to those that are carrying strategy ui of those that I've observed at time th. And so this probability is the fitness of the strategy at that particular occurrence measurement divided by the average fitness. There's a bar in the denominator there, all right? Whereas the uniform probability of selecting an agent whose strategy needs to be suppressed is just 1 over n for all the agents in the population. And so if I collect all of them just to see the probability that any random individual is chosen belonging to population that has UI as a strategy, is that expression there. And I just count the individuals who have the strategy uj for the suppression. So basically, these are the two probability measures that I need to look at. And now I want to see the following thing. I assume that one individual carrying strategy UI is chosen, and I measure that, and then one carrying strategy UJ is selected for suppression. And basically, this is the transition probability from the state lambda hat to the new state lambda hat, where I have one extra element in the I compartment and one fewer element in the J compartment. I need to average them out by 1 over n, and that's the thing that I need to look at. And multiplying the two things that I computed before, the probability of switching, like that one agent with strategy UI imposes their strategy on the agent that was previously carrying UJ, is precisely the last item there in the equation. Okay. All right. So far for the Moran process, it was a little bit maybe technical to follow, but I think I spent a little bit more slides on that one than on the replicator dynamics, because I always need to think carefully about random variables and occurrences and realizations and all that. So now it's time we've got all the elements level with the weights, the proportions. I can do a piecewise affine interpolation of the lambda at time steps th, and then you obtain a curve from 0 t defined on the time interval. And then I go back to the sequences that I mentioned already before. And the question now is that the lambda k is a little bit too weak to describe an evolution, and it doesn't have enough regularity from the technical, say, purposes. So basically, it's convenient to study the evolution of distributions of proportions, which means taking a probability measure over that space, and you can construct it in this way. So if you take the lambda k as a piecewise affine curve and you do the push forward of the reference probability measure, then I got something that I define capital lambda k. And then I can do the piecewise constant interpolation of that by taking the values that it takes at the left-hand side of the left-hand endpoint of the interval th plus 1. So lambda k with the bar, which is the piecewise constant, is easy to draw. The push forward of the other one, I'm not so sure, but their distance becomes arbitrarily small. Actually, they converge to one another when k goes to infinity. The good way to measure distance between probability measure is the one Wasserstein distance here, which is obtained basically by testing against the one Lipschitz functions, and here we can really make use of the update rule of the proportions to estimate the difference. Okay. So I've got this. Basically, if I take the piecewise affine interpolant of the curve on the simplex and I do the push forward of it, or if I take the piecewise constant approximation of the evaluation map, then I have measures that converge to one another. Then become arbitrarily close. And now this is the crucial thing. So I want to say that at each time step tau k, so for each given k, my curve of probability measures big lambda satisfies an approximate continuity equation. And in the limit, the error will go to 0. So in the limit as k goes to infinity, the wiggles will disappear. And to make the wiggles disappear, we need to use the hypothesis on the scaling of wk and nk with the time step, basically. So here, what do? I take basically a smooth test function defined from minus infinity to like that. So what I want to see is that I see, like when I integrate by part for the time derivative, I get the initial measure here. I see the test at the initial time, which is what I want to measure. And then I don't see anything at the final time. And when I transfer the partial derivatives on the test function, here I need to have a suitable notion of differentiability. In this case, it's pretty okay because it's just vectors. So time variable is one-dimensional and lambda is a vector in the simplex, so that's okay. And the wiggle there is encoded in this remainder row k, which is quantified in that way. So green objects are good. They will do whatever I want them to do, so they vanish, basically. And the red object is the nasty one in a way that strictly bigger than 1/2. So the proof of this proposition is really, really technical, but you need to use the equation to and the rule of update to estimate the error. And interestingly enough, and this is one objection that has been raised already, I need to control the L infinity norm of the gradient of phi twice. So just the same object, but then also the second order derivatives come into play. And the second order derivatives disappear just because I require alpha bigger than 1/2. If they didn't disappear, then that term here would remain. And when I do integration by parts, I would expect a second order derivative in the equation. So instead of ending up with a continuity equation, I would probably end up with something that looks like Fokker-Planck. Like you get a second order term which calls for a Laplacian there. And indeed, there are models. So for instance, when you put noise, if you have deterministic dynamics, which is altered by the Brownian motion, in which passing to the limit, you can definitely derive a Fokker-Planck equation. So it's all consistent. The point is that at this stage, we need to get rid of the second order derivatives just to get a first order dynamics, such as the continuity equation. And one other thing that I want to stress here is not in color, but with the field B is in the right-hand side of the replicator equation. So this B here is the one that was in the first slide about the replicator equation. So the one that measures how good my strategy does with all the others. Okay, so the theorem is this one, and maybe I can spend a few moments to describe something about that and make some comments later. We could prove that with a bunch of hypotheses that converges to infinity, there exists a subsequence converging to a solution of the continuity equation there. Okay, with initial distribution of the 0 given. So the interesting thing is that when you've got this structures, usually you want to prove a compactness argument. You want to obtain a compactness argument, but here it's really not immediate because you want to estimate something with respect to two time instance S and T. If they fall in the same little interval, which is wide tau k, everything goes fine. If they fall far apart, then you could concatenate the estimates. So you go from S to the first node of the partition, then you do a finite number of partition items, and then you would just go to T. But there's no way in this case to control uniformly the number of intervals that stay in between the S and T. So the usual Ascoli-Arzelà theorem cannot be applied. On the contrary, we could prove that if we kind of reprove it just for our case, we get compactness. So it cannot be used just as it is, but it needs to be reconstructed, being careful about some particular estimates. So with that, we get the integrals will converge well. and rho k equals to 0 thanks to this assumption there, because what's left after I use that alpha plus beta is equal to 1 and I even out the exponents of tau k is precisely this one. So I get one extra factor of 1 over n in front of the first derivatives in the first little o thing, a w in the numerator in this other term, and then this one definitely vanishes if alpha is bigger than 1/2. So there's no contribution whatsoever of the second order derivatives that needs to be taken into account. And this one, as I mentioned, as I announced at the beginning, is indeed the Eulerian formulation of the replicator equation, which was dealt with in these papers. So I think it's maybe time to wrap up and conclude. Maybe I'm a bit early, but I think it's fine. What we did here was to study this problem with a finite number of a finite number of strategies, and an interesting outlook would be to look for a countable number of strategies, or even a little bit more. So go to U being a compact metric space, as I announced. For this, functional analysis needs to be invoked very strongly, and when you take the partial derivatives for the weak formulation, basically, like this gradient here needs to be taken with respect to a variable lambda, which is a probability measure this time, and not just a point in the simplex. So that's probability measures live in a Banach space, and so suitable notions of Rashid differentiability need to be introduced. And for the first order part, it's done in the paper with Ambrosio, Fornaziere, and Savare. Possibly with the second order part, it requires a lot more effort. And just to touch base with my previous results, so one could look at, especially in homogeneous case, so put spatial dependence and see how the positions of the players when they move around come into play. And I say here agents can move on the graph because the interactions are basically can be described by the graph of each individual is connected to each other one, all right? And so for alpha equals 1/2, I mentioned here that there are formal results that are already available in the literature by some Portuguese or adopted Portuguese people. So Fabio Chelub is a Portuguese mathematician, and Leonard Monsaint-Jean is a French one, but is in Lisbon at the moment. And they formally prove that you do get the Fokker-Planck equation that I mentioned before. But the arguments are I think so basically what they do it for two strategies. So where then the simplex is just an element in 0, 1, basically, like the lambda, the weights are lambda and 1 minus lambda. So you can reduce everything to the unit interval. And if you want to have a little bit more sophistication, then again, some thoughts need to be put into this. And I think that the limiting equation with the Laplacian is called the Kimura equation. When you have basically two strategies, the weight B that you put in from x1 minus x type of thing. And so this motivates my desire to study second order dynamics, which is on the way to be addressed. So with this, I would like to thank you for your attention, and I'm happy to take any questions if you've got some.